Hello, welcome all. In this lecture, we will be dealing with the applications of residue theorem in complex analysis. We saw that Cauchy's residue theorem is a very powerful theorem which enables us to calculate closed integral of function uh, which has a number of isolated singularities within the area enclosed by the curve C. Right, and we saw that closed integral C f of z dz is nothing but 2 pi I times the sum of the residues of f at various points, singular points, right, all the singular points that it encloses. And we also saw that this all other integral theorems and formula that we came across are just forms a special part of this particular theorem, right? For example, if you only have one pole order n, then basically you can calculate closed integral C f of z divided by z minus z0 raised to n plus 1 dz is something like this, right? And this is nothing but the Cauchy's integral formula. Suppose there is nothing, there is no pole inside, then it's easy to see from here itself that if the f of z is analytic on and inside simple contour, then the closed integral vanishes, right? This was nothing but the Cauchy-Gauss theorem that we saw earlier, right? So residue theorem is very powerful and it is a general case, and one should expect a function having singularities in some region, right? Okay. Now we will be dealing with applications of residue theorem, okay, and we will be using the residue theorem to evaluate complex integrals and some real definite integrals using contour integration. We will do it through examples. Complex integrals, for example, what we were considering till now, right? Consider an integral of the type I1, which is a closed integral of 4z plus 3 by z into z plus 2 dz. Now the path C, say it is a circle with a radius 3. Right, this is a pretty simple normal integral, except that it has the area C it contains, which is a curve of which is a circle of radius 3, and you can see that the function has two simple poles, one at z equal to 0 and z equal to minus 2, right? And you can see that both of them lie within C, right? Till now without residue theorem, we were dealing with the integrants which has only one pole, in one is singularity inside the C, right? Now we have two singularities, and you can see that both of them are simple poles, right? And both lie within C. Now we can apply residue theorem, and it says that I1 will be equal to 2 pi I times all the residues that is included in C. So basically R of f0 and f minus 2. Now we need to calculate the this residue, just we need to calculate this residue, nothing else, that the integral is solved, right? Now how do we calculate the residue? We saw that residue of a function f at zi is nothing but limit z goes to zi 1 by p minus 1 factorial d raised to p minus 1 dz raised to p minus 1 z minus zi raised to p into f of z, right? Where p is the order of the pole, right? Now in our case p is equal to 1, right? If p equal to 1, then this also we saw that this above formula reduces into a very simple form, right? So in our case we have to use this simple formula only, and then for z1 equal to 0 and z2 equal to minus 2, we have to find the residues. Now you can see for z1 you can find the residue just using the formula, and you will get, with the easy cancellation, you will get 4z1 plus 3 by z1 minus z2. Now you substitute the values of z1 and z2 there, you get the residue at f of 0, which is nothing but 3 by 2. Similarly, you can do a calculation for f of z2 r at a residue of f of z2, right? And it will turn out to be nothing but 4 z2 plus 3 by z2 minus z1, and that will be nothing but 5 by 2. Now that means for this entire integral, we already have everything that we need to know to apply Cauchy residue theorem, right? We understood the curve, we understood the singularities, we understood the residues that is involved in the calculation, we obtained everything. Now it is just applying the theorem. So that is I1 is equal to 2 pi I times r f of 0 plus r f of minus 2. Just adding that, it gives 8 pi I. So that is the answer for your integral. Now let's take one more example, which is consider the integral I2, which is integral c sin h z by z raised to 4 dz. Okay, so, the c is same, that mod z is equal to 3. It's a radius of it's a circle of radius 3. Now one can note that this function, if you really note, this function has a clearly this function has a singularity at z equal to 0, right? Which is but suppose we naively it may think that z raised to 4 is a pole of order 4, right? But we don't know, because this function has to be dealt with care, because sin h z also has powers of z in it, right? Now suppose you are not very sure about the value of order of the pole here. You cannot use the formula that we have just seen, which contains for which you need to know the order of the, right? So this time let's calculate the residue in a different formula. How do you do that? You just expand it in a Lorentz series, right? So if you expand f of z in a Lorentz series, which is here, it is very easy, that 1 by z raised to 4, and then you just put in what in sin h z, which is z plus z cube by 3 factorial and all other things, and this is what you will get. Now once you get a Lorentz series of f z about z equal to 0, then you can easily read out the residue, right? Which is what is shown in the magenta. I mean, like, it will be 1 by 3 factorial, right? A inverse a of minus 1, which is a residue, and you can directly see that this is what the residue is. Also one can see that the order of the pole, the order of the largest term in the denominator is 3, so the order of the pole is 3, not 4, because sin z also has a set. This method of obtaining residues is best if you don't know the nature of singularity at the point of interest. If the function is complicated and you don't know, then you cannot apply the simple formula, right? So in that case, I think you need to write down the Lorentz series and get the residue. In one way or other, you need to find the residue. Okay, so once you know the residue, then it is very simple, because z equal to 0 lies inside the C, right? And there's only one pole, that is at z equal to 3, z equal to 0, and that we know that the pole is of order 3 and residue is 1 by 6. Then you can blindly apply the residue theorem, which says that I2 is equal to 2 pi I times r of f of z equal to 0, which is 1 by 6. So that I2 will become I pi by 3. So by straightforward calculation, you can get the integral value of integral. Okay, so in this manner, if there is a complex integral that we have often seen, if your integrand contains multiple poles, you can deal with them in a very easy manner by calculating the residue by using this residue theorem. Now let us deal with something else. There are a class of real integrals which can be calculated using complex integration with the residue theorem, and which will be dealt with what is called as a contour integral. It will be clear what I am saying. Like, there are many types. Let's first consider the real integrals, with the integrands being sinusoidal functions. Okay, so an integral of the type, consider an integral of the type what I shown, j. Okay, 0 to 2 pi is the limit, and integration is on theta, and that f is a function of sine theta and cos theta, and or cos theta. F is some function like a rational function of the sine theta and cos theta. So this kind of an integral can be evaluated by what is called as a complexifying the integral and evaluating it as a contour integral. It will be clear when we try to do this as an example. Okay, the argument or the insight here is that if you carefully look at the integral, it is 0 to 2 pi d theta. So you can see that if you fix z equal to some radius and vary theta to 0 to 2 pi, you are actually getting a closed integral in z plane, right? So that is the clue. I mean, you take a unit circle and you say that, okay, 0 to 2 pi d theta can be converted into a circle in a complex plane. This is the idea that we will be using here. Okay, so integration can be casted around a closed circle with fixed radius. Then we can apply z is equal to e raised to I theta, polar form, right? R equal to 1, radius is 1. If that's the case, you can see that d theta is equal to minus I z inverse dz, and sine n theta is nothing but z raised to n minus z raised to minus n by 2, and cos n theta is z raised to n plus z raised to minus n by 2. And you can substitute this integral, substitute these values into the integral, and then the integral becomes just a normal integral, complex integral that just we saw. Okay, we can apply residue and then just residue theorem and then calculate the value of the integral. It will be becoming clear when we do an example. So consider this example. We are evaluating j1, which is 0 to 2 pi d theta by a plus cos theta, and the condition is given that a is greater than 1. That's the condition you are given. So again 0 to 2 pi d theta, so everything looks fine. So we can complexify it by following substitution, right? Only cos theta is involved, so z plus z minus 1 by 2, there is no sine theta involved, so it's easy. If you put this substitutions into the integral, what we get is j1 is equal to closed integral c. Now the closed integral c is nothing but a unit circle, right? Mod z equal to 1. This is what the new contour looks like, right? Now j1 becomes minus I'm just substituting directly into d theta and what I cos theta are, and then what you will get is this value, right? Rearranging it, I can write it as 2 by I closed integral c dz by z square 2az plus 1. Now this is a very familiar thing that you just did, right? This is a normal contour integration, normal complex integration with multiple poles, right? It's a second order, so there will be 2 poles in it. So we can do it using residue theorem. So I hope the idea is clear that you are making a substitution when the limit is from 0 to 2 pi d theta, then you know that it can be casted as the real integral. This real integral can be casted as a complex integral in z plane with c being a closed circle, a circle. Okay. So j1 we saw it is like this. So next step is to find out factorize this so that we get the poles, right? So it's easy. You can see that you can solve it using the standard formulas, and then we will get dz as z minus z1 into z minus z2. And basically there are simple poles, and the value of z1 is minus a plus root of a square minus 1, and z2 is minus a minus root of a square minus 1. These are the 2 values that you will get. Okay. Now note whether these 2 values are lying within the contour. That is the next step. Okay. So you can see that the z2, which is minus a minus root of a square minus 1, won't lie within C, since a is greater than 1. You take any value of a which should be greater than 1, and convince yourself that z2 will never going to lie in mod z equal to 1 C curve. Okay, that you convince. Then you can see that this j1 has only one pole, which is at z equal to 1, which is a simple pole, which is going to contribute to the Cauchy's residue theorem. Okay, and that residue can be easily calculated because it's a simple pole with the formula that limit z goes to z1, z minus z1 into f of z, which can be easily casted in this form, and that we will get it as minus I by root of a square minus 1. Okay, now we know all the things. We can directly apply the Cauchy's theorem, residue theorem, and then what we get is J1 is equal to 2 pi I times R at f of z, and 2 pi I times minus I by root of a square minus 1. So the answer is we are getting. So you see, this complicated integral, we don't have to solve anything. We just need to find the very simple pole. I mean, we need to identify the pole and we need to find the residue. That's it. You don't have to worry anything about the integral, right? We will take one more example in this sinusoidal type, and we will try to do it. Oh, now let's consider this integral, which is 0 to 2 pi cos 2 theta by a square plus b square minus 2ab cos theta d theta, with the condition that b is greater than a and a is greater than 1. Okay, clearly this is a function, this is a rational function, and you can see that again the limit varies from 0 to 2 pi, and the integration variable is d theta, right? So you can directly substitute the conditions, which is like d theta equal to minus I z minus I z inverse dz, and cos 2 theta here cos theta will be there, which is nothing but z plus z minus 1 by 2, but cos 2 theta it should be z square plus z raised to minus 2 by 2. Okay, again in this type of calculation c is always mod z equal to 1. Okay, so this integral, if you substitute this and work out little bit here and there, this J2 becomes integral in the complex plane with I by 2ab more closed integral c z square z raised to 4 plus 1 into z square z minus a by b into z minus b by b. Clear? So it is clear that there are three singularities, three poles for this integrand. One is order of 2, that is at z1 equal to 0, and two simple poles at z equal to a by b and z equal to b by a. We should note that the z3, which is b by a, is not going to contribute because it lies outside unit circle, right? B is greater than a, which is given as the condition. So b is this condition is given, so this point is not going to contribute. Okay, now then we can write down the residue theorem, which is J2 is equal to 2 pi I times R of fz1 plus R of fz2. Z3 is not going to contribute. Now it's all boiled down to calculating the value of the residues R at fz1 and R at fz2. Okay, so this is the function that we have, I by 2ab, and we need to calculate the residue. There is no simple way here. There is first and foremost we have to find the order 2 pole at z1, which will be R of fz1, and the formula we have to use, limit z goes to z1 d by dz of z square f of z. You do the algebra, you do the differentiation, you do the algebra, and you make the substitution that z equal to z1. What you will get is what I wrote, I by 2ab, a by b plus b by a. Okay, now second order 1 pole at z2 a by b, which is again simple, limit z goes to z2, z minus z1 by f of z. This is what the formula is, right? Sorry, z minus z2 has to be here, so f of z. So this will be equal to, again you substitute and you make the substitution, z goes to z2, basically you will get something like this. So this is again very simple. So you got two residues that are required to complete this calculation. So again you can take J2 is equal to 2 pi I times R at fz0 plus R at fz2, right? You add these two residues and multiply by 2 pi I, this is what you get, and this is the answer for your integral. So again you saw that by sinusoidal type, in sinusoidal type integrands that we considered, we can make just a substitution, we can transport everything into complex plane and with the c being mod z equal to 1, you can do the calculation easily, and you can write down the answer using residue theorem. Okay, so again I'm just saying what we did was we took a real integral and we solved it in a complex plane. Okay, this real integral, otherwise some of these real integrals are very nasty to solve when you are considering only in using some other methods. So advantage of this is that, so I will say that when people do complex analysis problems, especially this kind of integrals, you try to work it out in the in the real coordinates itself. I mean, not in the complex plane, and you will try to see how difficult it will be. Okay, now we will go to the final set, which is that we are going to deal with the real infinite integrals of rational functions of the type k is equal to minus infinity to infinity, minus is missing, minus infinity to infinity p of x by q of x dx. This type of integrals can be handled using complex contour integration, provided nature of px, qx are real polynomials. Px and qx has to be real polynomials. Not only that, degree of the polynomial q has to be at least greater than that of px by 2. Okay, so if the degree of the polynomial p is 3, q has to be minimum a polynomial of degree 5. A minimum 2, there should be a difference of the degrees with the number 2, otherwise this will not work. Okay, not only that, another condition is also needed, which is that q of x is not, for any real value of x, q of x won't be 0. Okay, q of x, if you are writing this integral and you are finding the pole, you have to write q of x equal to 0, right? That should not give you a pole which lies in the x-axis. Okay, so if these three conditions are met, we can handle this integral, any real integral of this sort of type, using complex integration, using residue theorem. And additionally, if px by qx is even, then you can even handle the integrals from 0 to infinity, right? So that is obvious, that, and we will see how it is done. Okay, so this is interesting. Let's see how we are going to do this kind of a integral. Here we won't make any solution. In fact, what we will do is we will start with a complex closed integral, and we will get the desired real integral, that is this type of an integral from it, through cleverly selecting the contours and applying the residue theorems. Okay, we will see it through an example. So what we will do essentially is, suppose this is the contours, these are the residues that you are getting. These are the points of singularities that you have, suppose, for f of pz by qz. Okay, so first what you will do is, you will, instead of px by qx, you will consider a closed integral pz by qz. Okay, x goes to z. Okay, so that's what we will do, and contour will be taken like this. We will take a semicircular contour. Okay, always, so that this entire C, which is this closed contour, can be divided into two types of contours, one running from minus r to r, okay, through the straight to the real x-axis, and then another one is the gamma integral, which is going through a semicircular, it's going through a semicircle of radius r. I hope that is clear. You see, we will consider, instead of an integral of this sort, a real integral, we will begin with the complex integral, which is a closed complex integral C, and the C is defined like this, so that you can write it as minus r to r, and over this pz by qz is nothing but px by qx, because the imaginary part is 0 here, right? So minus r to r px by qx dx, plus, that is this part, then this part is a gamma integral, integral over gamma pz by qz dz, right? So this is perfectly fine. You can take an integral of this sort, and you already know that you have stated that qx doesn't have any singularity over the real axis, so there is no singularity in this region, and all the singularities are inside this R. You will choose your R such that all the singularities lie within R. Okay, if that is always you can do that. If that is the case, then you can write the closed integral like this. Now this closed integral is by residue theorem is nothing but 2 pi I times modulus 2 pi I times the residue of this function, right? Of the summation is over all the poles inside the semicircle with radius R in upper half plane, right? You take R in such a way that it encloses all the poles, right, within the R. So this is fine. You can so the integral is equal to this. I hope it is clear. So what we did, we started with the px by qx, we transported that into a complex, we changed into a complex integral, closed integral pz by qz and dz, and c we define like one section from minus r to r and another section through the semicircle gamma, right? And we wrote that this entire thing will be nothing but the 2 pi I times this residue of all the functions, all the points. For illustrative purpose I have just kept 3, but all the points. Remember this only condition is that qz or the integrand doesn't have a pole on real axis. It can have in imaginary axis, no issue. It cannot have in the real axis. That's the only condition that we put in. Okay. So now you can see that what we is integral pz by dz. This is which if we take the limit r goes to infinity. Okay. If we take r goes to infinity, then essentially you can see that this becomes minus infinity to infinity, right? And here this becomes minus infinity to infinity, and this contains all the planes. So basically we are expanding our integral in all over the upper half plane, right? And not going below this, but if you increase the radius, basically everything is getting increased. This is from minus infinity to infinity, and here also the gamma integration is over the a semicircle which having an infinite radius. Clear? And always before giving r equal to infinity, you can always substitute the gamma integral like this. P in gamma in this complex in this semicircle, you can always substitute z equal to r e raised to I theta, right? If r is if z is r, if it's in a semicircle, in gamma z is always r equal to z equal to r e raised to I theta. So I am just substituted that in gamma. I just substituted that, and I wrote it is 2 pi I times the thing. Now it can be shown that for the conditions we assigned for p and q, like that they have to be polynomials, and you know that there is a degree difference of 2 between q and p. The integrand over the semicircular path will go to 0 as r goes to infinity. This can be shown. Okay, we will show that. Okay, and thus if that is the case, essentially we got the integral that we were looking for. Is that clear? What I am saying is, if we put the condition r goes to infinity here in this integral, look at this integral. If we put the condition r goes to infinity here, what we will get is this first part integral is becoming k, which we started to find out, which is what we are starting, which is what we want to find out. And the next second integral, which is p of r e raised to I theta by q of r e raised to I theta, and dz is nothing but r e raised to I theta d theta. This particular integral, I claim that, and we will show that this will go to 0 for the conditions that we specified for px and qx, right? And this summation now is over all the upper half plane. We already started with r, which includes all the residues. So this you have to find out all the residues in the upper half plane, and then you can multiply it by 2 pi I. So essentially you will get the real integral. So I hope the trick is very clear. We wanted this, right? This is what we wanted. So you can cleverly see that this can be casted like this in x-axis, and then you took a complex integral, which is you manipulated your contour in such a way that it is along a semicircular path, right? Then you calculated the residues inside this. Then without, if that is the case, then you very well know that you don't have to calculate the integral. You can just write down the value of the integral of this closed C as 2 pi I times the residues, right? And you put a infinity, you allowed r goes to infinity, so that it becomes minus infinity to plus infinity. This is what we wanted, right? And for such p and q, it is always seen that this other part of the integral, the non-trivial part of the integral, which is around gamma, goes to 0. So by a clever manipulation, you got the desired integral, the real integral, as a by just evaluating the residues. We will do this. We will explicitly show how it goes to 0 and all through examples, when it will be clear. First, consider the following example. Okay, k1 is equal to minus infinity to infinity dx by 1 plus x square. Okay, this integral can be solved in different ways also, but for illustrative purposes, let us take this simple integral. Now, with p of here, p is 1 and q is 1 plus x square, right? So you can see that there is a difference of 2 in the degrees, and all the required conditions are satisfied here, right? Now we can consider the semicircular path in the upper half plane, so that you consider first a closed integral C dz by 1 plus z square, right? And then you integrate it from minus r to r dx by 1 plus x square, and then you use a gamma. So this is in the real axis and this is in the semicircular one. And you know that by Cauchy's residue theorem, this is equal to nothing but 2 pi I times the residues involved, right? Okay, now let's consider the gamma integral for a specific case. So dz by 1 plus z square. So gamma is like having a radius r, so you can substitute z equal to r e raised to I theta, a fixed r. So this becomes r e raised to I theta, I d theta, and 1 plus z square becomes r square e raised to 2I theta. Now imagine what happens when r is very high, very large. If r is very large, actually you can neglect this one compared to the huge value of r, right? So approximately you can take out, you can neglect this, then it becomes 1 by r times 0 to pi. Remember, this integration is from 0 to pi, not 0 to 2 pi, right? Because you are only considering in the considering only upper half plane. Okay, so 1 by r and 0 to pi some theta integral, right? Now no matter what the value of this thing is, as r goes to infinity, this will go to 0 because there is a 1 by r sitting. Clear? So what we did, we took a gamma integral and then we substituted z equal to r e raised to I theta. Then for large values of r, you can take 1 by r out, you can neglect 1 here. Then as r goes to infinity, you can see that it doesn't matter what is the value of this, it will go to 0. Good. So what we saw is that the closed integral C dz by 1 plus z square is equal to 2 pi I times the residues, right? So then we factorize 1 plus z square, and it's very easy, z plus I and z minus I, and that will be equal to this. And in our case, we just need to consider this pole, right? Z equal to I, because z equal to minus I is not in the upper half plane, so we are only considering upper half plane things for this purpose, right? So that this is equal to, for example, if the gamma integral goes, this is nothing but a real integral, minus infinity into infinity dx by 1 plus x square, that is 2 pi I times residue at p of I by q of I, right? Now that can be for this simple pole, you can again use the formula that we are familiar with, and then you can calculate it very easily. You will get it as 1 by 2I. Okay, so once you get that, then this is trivial. K1, which is what we looked for, is nothing but 2 pi I times 1 by 2I, so that is nothing but sorry, there won't be any I, so pi. Okay, the answer will be. Now consider another function which is a bit more complicated. Okay, so k2 is nothing but 0 to infinity x square 9 plus x square into 1 plus x square. Okay, so first and foremost note that this integral has a limit from 0 to infinity. Okay, dx is missing, but 0 to infinity, right? So let's see, if that is the case, you can see that this entire thing is even, right? So you can write it as 1 by 2 times minus infinity to infinity x square by 9 plus x square into 1 plus x square dx. This is in the form that we know. Okay, so since because of this is even, this integrand is an even function, you can always write like this. So this is what I said when minus infinity to infinity integrals and 0 to infinity integrals for even functions can be handled in this manner. Okay, now look, p of x and q of x satisfies our condition. This is 4 and this is 2. Okay, now we can proceed constructing the semicircular path in the upper half plane, right? So close integral c, you complexify it, z square dz by 9 plus z square plus 1 plus z square equal to minus r to r, this, and the integral over the semicircle, and not minus r to r is already a real integral, dx is missing here. Okay, and this all is equal to 2 pi a times residue of p of zk by q of zk, which is nothing but this, right, this function. Okay, now let's consider what is going to happen with gamma. Okay, now before that let's first evaluate this residue itself. So you can see that the integrand has two simple poles. Integrand has two simple poles, right? How many singularities are there? There will be 4 singularities, but only 2 of them will be in the upper half plane, right? And what are the singularities that is gonna come in the upper half plane? Z1 equal to I and Z2 equal to 3I. There is another set 3 which is at minus I and set 4 at minus 3I, which is not going to contribute, right? And the corresponding residues can be calculated easily. For Z1 you can calculate it using the formula. It's a simple pole, it's very easily you can write out, it will be minus 1 by 16I. Okay, now we will calculate for pz2, which is a 3I, and that is also can be easily calculated without any difficulty, and which will come out to be nothing but 3 by 16I. Okay, so now let us look at the gamma integral that we were looking. This is the gamma integral. Let us look at what happens to the gamma integral. Okay, now gamma integral, if you take z square dz by 9 plus z square 1 plus z square, you can substitute again z equal to r e raised to I theta. So basically you will get all these terms in the numerator and all these terms in the denominator. Again, when r is pretty large, huge, you can neglect this 9 and 1. So you will get something like r raised to r cube here and r raised to 4 here. So essentially 1 by r again will come, and there will be a theta integral. Never bother with that in theta integral, whatever be the value, since there is a 1 by r term sitting, and that will make sure that the integrand goes to 0 when r goes to infinity. Okay, so we have done, like there is nothing left. We showed that when you have the in this complex z squared dz by 9 plus z square 1 plus z squared integral over c, close integral over c, you saw it as nothing but at limit r goes to infinity, there is a minus infinity to one real part, and then there is a complex part, and complex part in the semicircular in the semicircle it goes to 0, right? In the not when c is not in the real plane, real axis, it goes to 0, right? And this integral, you can apply the Cauchy's theorem, and it is nothing but 2 pi a times all the poles that is lying in the upper half plane, which is, you can directly write down, it's at pi by 4. Fine. So Note, okay, not done completely. You remember this is minus infinity to infinity. This is not what we wanted. We wanted 0 to infinity, right? The integral that we found is from minus infinity to infinity, is an even function, but what we wanted was nothing but 0 to infinity, right? So you have to divide 1 by 2 for this over this integral to get the answer, final answer. So the final answer is pi by 8. Don't miss it. This is important. Okay. So you can see that we have calculated using residue theorem. We have calculated three types of things. One is simple complex integrals, right? Another one is what we have is the type complex integrals, and another one was the type of sinusoidal functions, which is of this sort of thing, and where we saw that we can substitute with this kind of substitution, it will make sure that this goes into a complex integral. This goes into a complex integral over a closed curve, so mod z equal to 1, right? And then we can do it as a normal complex integral. How will you do that? You just apply residue theorem. You calculate the residues within C, and then you apply the residue theorem, right? Then we saw a third type, which is that integrals of rational functions of this type, right? Minus infinity to infinity, px by qx dx. Here with these conditions, remember the conditions, make sure the conditions are met, otherwise you won't be able to do. Why? It's clear, because otherwise the gamma integral won't go to 0, right? There will be some value for it. As r goes to infinity, gamma will always blow, right? That is the reason. So if these are met, you can actually divide your you can consider the entire integration in a complex plane with a closed contour like this, where you will make sure that the one part is from minus r to r, and another part is over this semicircle, and with these conditions this part will not contribute, so only this will remain, and at the limit r goes to infinity, this is nothing but the desired integral. So these three types of integrals we saw how we can do with residue theorem. These are the applications of residue theorem that we need to know.